So in the previous video, I briefly introduced the notion of Riemann sums and how we can use Riemann sums to approximate graphically the value of definite integrals for slightly more complicated functions where we can't really use our knowledge of analytic geometry, right? And essentially what we did for Riemann sums, we just kind of partitioned the x-axis into very small base lengths, and we used the value of the function as kind of the height for each of these base lengths, and we constructed rectangles beneath the curve and above the x-axis to kind of partition this entire area beneath the curve into a bunch of small rectangles in which we summed up all the areas of the rectangles in order to approximate these definite integrals, right? And so now we're going to go ahead and continue this notion by looking at particular types of Riemann sums. And so generally we have two types of Riemann sums. We have the left Riemann sums and we have the right Riemann sums. And we're going to kind of go ahead and compare these two different Riemann sums side by side to see how they differ from each other and how we would use one over the other and the certain circumstances in which we would use the left Riemann sum, the circumstances in which we would use a right Riemann sum. And so let's go ahead and actually do that. And so suppose we wanted to evaluate the same integral as we were looking at, or the same definite integral that we were looking at in the previous video, right? The integral from 1 to 3 of x squared dx. And so this right over here is a kind of short sketch of f of x equals to x squared. And we wanted to determine the integral, the definite integral from 1 to 3 of this function, right? And so if we wanted to use a left Riemann sum approximation, the first step we would do is we'd go ahead and first of all draw out our boundaries. So let's go ahead and do that. So we're looking at this interval of the real line, so from 1 to 3. Okay, it's not very good. So from 1 to 3, looks something like that. And for a left Riemann sum, what we're going to do is we're going to use the value of the function on the left-hand side of each partition in order to function as our height for each individual rectangle. So let me go ahead and show you what I mean by that. So let's say that we want to divide this up into 4 individual Riemann sums, right? We can use however many we want, but for the sake of convenience, let's just use 4. And we don't necessarily have to have these 4 Riemann sums with an equal kind of, we don't need to equally partition the x-axis into kind of equal lengths, right? We can make the length however much we want. They don't necessarily have to be equal, and in some circumstances it actually might be better if we don't use equal lengths. But for the sake of this video, let's just go ahead and partition it into 4 equal lengths over here. Right, so here we have the base for 4 individual rectangles. Each of them are of equal base length. And what we're going to do for a left Riemann sum is we have two kind of sides of our function that we could use as a height. We could take this side right over here, which would be the right of this little rectangle, because this is our base over here. On the right-hand side of our base, we would have one possible kind of value of our function for the height of each rectangle, or we could use this side over here, the left-hand side. And as you can imagine, in a left Riemann sum, we're going to use the left-hand side of each individual partition as the height of our rectangle. And so let's go ahead and show that. So we would use, this is the height for this first rectangle over here. For this second rectangle, we could either use this height on the right or this height on the left. Again, we're using a left Riemann sum, so we're going to go ahead and use the left-hand side. Same thing for this one over here. And finally, for this rectangle right over here, right? And so now we have each individual base length, right? We have this base length, we have this one, and we also have this one right over here. And each individual base length has a corresponding height, and each height happens to be the value of the function on the left-hand side of each individual partition, if that makes sense. And so then what we would do is we would go ahead and calculate each individual area, sum them up, and we would get an approximation of our definite integral right over here, right? And so we know that each of these points, each of these heights is going to be the value of the function on the left-hand side of each partition. So if we were to calculate the area, right, if we were to approximate it, it would be equal to essentially the base length times the height. So the base length over here, we know that each of these things represents 0.5, so this would be 2.5 over here. So we know it's going to be the base length, which is 0.5, right, because we have from 1 to 1.5, that's 0.5. From 1.5 to 2, again, 0.5. So each individual base length is 0.5. And we're going to multiply that by the height. And the height is the value of the function at the left-hand side of each individual partition. So over here, this height, right over here for this rectangle, would be, in fact, f of 1. And then we're going to add that to the area of this rectangle. For this rectangle over here, again, the base is 0.5. The height is the value of the function on the left-hand side, which would be f of 1.5. And then for the next one, for this rectangle over here, it would be Again, 0.5 is our base times the height of the function, or the height of the rectangle, which is the value of the function on the left-hand side of the partition, which is f of 2. And then for the last rectangle, again, this one over here, base length of 0.5, and our height is the value of the function on the left-hand side of the partition, so times f of 2.5. And then you could go ahead and calculate that, and you'd get an approximation of this integral right over here, of this definite integral. And as you can imagine, the smaller and smaller the base length, the more accurate your approximation is going to be, because you're going to have more rectangles that are kind of fine, that have finer partitions, and so you would end up with a less margin of error. Because here you can see we have a pretty good bit of area left over that is going unaccounted for in this Riemann sum. And so what about a right Riemann sum now? Again, it's basically the same exact notion as a left Riemann sum, but instead of using the left-hand side of the function as our height, we're going to use the value of the function on the right-hand side of each partition as the height. So again, let me go ahead and draw out the interval that we're looking at. So this is going to be from 1 to 3. That's not very accurate. Okay, there we go. And again, we can divide into 4 subdivisions. Again, we can use however many subdivisions we want. I'm just going to use 4 for the sake of this video because of the way that I drew out the x-axis over here. And again, we're going to make them of equal base because just for convenience sake, really. And now what we're going to do is, so each of these still have the same base length, right? Each of these base lengths are 0.5 in this particular case. Again, they don't have to be equal, and they obviously don't have to be 0.5. You can use whatever base lengths you would like depending on the circumstance. But now we're going to use for the height of the function, instead of using this point right over here as the height for this rectangle, we're going to use the value of the function over here on the right-hand side of the partition. And so this right over here, this would be our rectangle. Same thing for this thing right over here. We could either use this point over here or this point right over here, but we're going to use the point on the right-hand side because we're using a right Riemann sum approximation. So that's not very... Okay, so our rectangle would look something like that. Same thing for this point right over here. We would again use the value of the function on the right-hand side of the partition as the height. Same thing for this point right over here. And that would be our Riemann sum kind of drawn out right over there, a representation of our Riemann sum. And so now we're going to do our total area in this circumstance is going to be given by, again, the base length, which is 0.5. So the area of this rectangle, the base length is 0.5. And we know that the height is now going to be the value of the function on the right-hand side of our partition. So f of 1.5 in this case. Same thing for this rectangle right over here. Base length of 0.5 times the height of the function, which is the value of the function on the right-hand side. So f of 2 on the right-hand side of our partition, I should say. And then for this rectangle right over here, again, base length of 0.5, the height is going to be f of 2.5, right? The value of the function on the left-hand side of the partition. And finally, for this rectangle right over here, we have a base length of 0.5, and the value of the function on the left-hand side is going to give us our height. So it's going to be f of 3. And so as you can see in this case, now we have a bit of an over-approximation, right? Because we have these areas right over here that are kind of above the function, right? So now our Riemann sum is a bit of an over-approximation. So you're going to use a left Riemann sum or a right Riemann sum depending on the circumstance and depending on, kind of really the margin of error. If you're trying to minimize the margin of error as much as possible, or trying to minimize the kind of amount of area that's unaccounted for or that's over-approximated, then you'd use either a left Riemann sum or a right Riemann sum, again, according to the circumstance. And in the next video, we're actually going to go ahead and evaluate, or at least approximate, a definite integral using this notion of Riemann sums. And so I hope this kind of clarifies the 2 types of Riemann sums that you would have in a Calculus 1 course.